Okay, and let's go back. I should put it here. Okay, everything should be set. Okay, so last time we talked about this idea of density matrix. I guess I should go to very beginning of the slides. Okay, so we have that the density matrix or density operator is defined as this quantity is associated with an ensemble of pure state. So if you have an ensemble of pure state, means that you have some pure state that come with some probability pi. Then you can define a density matrix or density operator that's just this average according to your probability pi here and those projector onto your state. So, or this outer product of those states. So this psi cat, psi bra. Okay. So this thing is a summation of a bunch of matrix and it's a matrix. And why is this important? Because we see that this density matrix tell us everything about this ensemble of pure state. So we check that they describe the evolution, measurement, and this ensemble of matrices. And moreover, we find out we have this. Moreover, we have this theorem saying that any matrix that satisfies two properties, that if they are trace one and they are PSD, then they can be you can associate with associate an ensemble with it. Okay, so we can forget about this ensemble interpretation and just describe any quantum system as this density matrix rho. They just need to be trace one and PSD. Okay? And this is a bit generalization of what our quantum mechanics before, because it also allows some classical probability. So remember from beginning of our of this chapter, we motivate this as saying we might want to have some classical distribution over our quantum states, and we see that it can be described as density matrix. Density matrices are matrices of dimension as same as the dimension of real Hilbert space, and they need to be trace one and PSD. And we rewrite all our postulates of quantum mechanics in terms of density matrix here. 1, 2, 3, 4. Okay. So those are density matrix, and then we quickly see that one of the biggest, one of the biggest application of density matrix is this reduced density matrix. Okay. So reduced density matrix is well, whenever you have entangled quantum state, you can describe one part of your system with this reduced density matrix. And so first we show how to calculate it. So, so we say that if we have any density matrix on two systems, so we have system A and system B, and we have a density operator on two systems, rho AB, then we can calculate reduced density matrix on system A by doing this partial trace operation over system B. Okay? And this partial trace operation is the next classroom or? Okay, I guess it's not else. Okay. Yeah, anyway, so partial trace operation is defined by, well, those two rules. First is that if you have this orderly tensor together, so those are non-entangled density matrix, then partial trace means that you trace on the B part. So you take a trace on B top, means that if you have something, some ket some bra, then will be that bra times ket, and this become number. They multiplying on your matrix on A part. And then you can then also we have linearity. So if you have some density matrix rho AB plus some density matrix rho sigma AB, then trace B on those sum equal to sum of those trace B. Okay. And yeah, we see some example of calculating this, and you see this is quite a cumbersome calculation. You have this beta 0, beta 0, 0, beta equal to 1 half 0, 0 plus 1, 1, and you calculate its reduced density matrix. Part A is this totally mixed state. It's 1 half 0, 0 plus 1, 1. And you see, well, if you are familiar with this, you can do this a bit faster because you see that when you do on trace B part, then the 0 component and the 1 component has the inner part 0. So those 2 terms will vanish. So you only need to calculate the 0 term and the 1 term, etc. Okay, and I guess this is a property that we'll use quite a bit today when we talk about purification and the stream decomposition. Okay, when you do partial trace on B, when you see we have a pure state here, and on the B part you have a 2 orthogonal state. Then you do partial trace, then the inner product between those orthogonal part is one inner part with 0, and this inner part 0 inner product with 1 will get cancelled, will vanish. Okay, so you only get this 0 part and this 1 part. And anyway, let's go back to reduced density matrix. And we say reduced density matrix totally describe what happened on system A. And so this means several things. Okay, so first thing is okay. So first thing is that when you do any measurement on system A, then it should so reducing matrix should describe all the outcome on your system. So we're now talking about row A. Okay. And so first thing we need to check is that this sigma A, sorry, this row A, describe all the measurement outcome on system A. Okay. And yeah, so we have a kind of a proof sketch here. Okay. Yeah. Yeah. So the proof is well, a bit of cheating because we use another property of a reduced density matrix. Okay. And anyway, so but I like this proof because it gives us a good idea of what reduced density matrix look at what it is. Okay, so the proof in quotation mark here is what we do is we say we have system A here, system B here, and we say if we just measure system B in computational basis, so just measure all becomes something, and then A will collapse into its reduced density matrix. And I guess here this measurement so I should say a little more. Okay, so what we mean measurement here is we measurement but without revealing the results. Okay, so we think A and B are far away, and B just do measurement. And as we know in the teleportation example, you do measurement on B, you will change the whole state. So that's the squeaky action at distance. So the whole system will get changed just by measuring on system B. And yeah, and so it will become this thing, right? So the whole system will become this post-measurement state. But then if we okay, and but if we didn't yeah, so B will get some probability of a different measurement outcome, and condition on different outcome, the state will become different state. But we also know now we know the density matrix formulation. We know how to describe something that without knowing the measurement outcome. Okay? So if we measure in B, but then B kind of just don't reveal the measurement outcome, then to A, his state got collapsed into something, but with different probability mixture. Okay. So what we are saying is B will measure something and without revealing results. Okay, without revealing results. And so you will have corresponding density matrix, post-measurement density matrix on system AB, and the density matrix will have the reduced density matrix that's row A. What did I say? The density matrix will really look like you have a reduced density matrix on system A. I guess it's easier to see the proof. So in terms of math, what happened is here. So we just measure system B in computational basis. Okay. And so measuring system B computational basis in terms of generalized measurement, that's doing the measurement with this measurement operator projector into computational basis I. And then because it's only measurement on system B, then the measurement operator is utensor identity on system A. Okay. and you will get a corresponding outcome with some example pi rho I a b. And so we can calculate this pi rho I a b, and it will be as we say is this rule we sum over. This is for particular I. So for particular outcome I, and multiply with probability pi will be you just sandwich your rho a b with your measurement operator. This IA tensor identity, and here we omit the a here. Okay, and then this thing will become this thing. I guess this is actually take quite some. If you want to prove this two here, and rigorously is a long line of proof. But ideally, you look at the A part and B part. So how should we say? So on the B part, we have this identity. Then B part it should be ICAT and eyebrow, because on B part, so everything. So excuse me, all the things on B part are. So here we have the B part, and here we have something on B part, here we have something on B part, and here we have something both on A part and B part. And so intuitively the B part should become, because we think A part multiplying A part and B part multiplying B part, so at the end the B part should become this cat I, and in the middle should be some number, and in the end it should be the also this I. But in the middle, this some number part actually become. So in the middle, we have this eyebrow times something times ICAT, and this means that the B part become a number. So if you sandwich this thing with rho A B, it actually become a matrix on system A. Okay. And yeah, we have more detailed calculation here, but that's ignore that for now. Let's assume this is true. So if you do this calculation, and we will see that it becomes something on system A tensor something on system B. Okay, and yeah, so we see that for every measurement outcome, we have that on system A is this thing. It's this identity tensor broad I times your rho A B times anti tensor cat I. Okay. And then we think, so we know that, yeah, and so if we discard the system B part, so system B only have the measurement outcome, and the system A has this weird matrix, then we see that the total matrix, so we know the measurement outcome has probability pi, and pi on the, so sorry, so this is quite confusing, so quite complicated. So this is rho A means the post measurement state, this is rho I means the post measurement state. So, I should start with rho AIB. So rho AIB is the post measurement state with outcome I, and rho A is the post measurement state of rho AB. That's only on the system A, because we see that this rho IAB is actually a non-entangled state. It's something on system A and tensor something on system B, and on the system B part is only this outcome state only says is outcome I. Okay, so if we throw away the system B part, then condition on outcome being I, the state on system A is only this I tensor identity tensor eyebrow times rho A times identity tensor IK. Okay, and so we know if we throw away system B, then and never reveal this result on I, then on system A we just have this kind of state. So this rho I and mixed with probability pi. Okay, so the total density matrix on system A should be sum over I pi rho I, and there is a summation this thing, and you see that it's exactly you doing trace B on rho AB. Okay, so this is kind of proof. And in this proof, we actually use another another property of density matrix. That is, we assume that if you do measurement on system B, that doesn't change the density matrix on system A. So I guess this is a bit of circular. Yeah, but I like this proof because it shows quite a nice idea about the reduced density matrix. You can kind of think of this partial trace operation as you just measure system B in computational basis. Okay, and yeah, so we here use a physical argument, which you can actually prove more rigorously with our quantum mechanics formulation. But another property of reduced density matrix is you do anything on system B, it should not change the density matrix on system A. You should not change the reduced density matrix on system A, because that will allow faster than speed of light communication. Okay, so yeah, so we think measurement outcome on system A is same whether or not you do computational basis measurement on system B. Okay. Any questions so far? If not, and yeah, I guess this equal sign here is quite confusing. So let's try to do this carefully to show that this is actually true. Okay, so we have this thing we want to show. Okay, this thing we have I tensor IK projected on I, and rho AB and I tensor projected on I. Okay, and yeah. So first thing we do is so now remember. So first thing we do is we do something very funny. Okay, so this should also be equal sign. Okay, we do something that we don't usually do. That is, we break these two matrices into product of two matrices. Okay, so we have I tensor IK IK I bra turn into I tensor IK times I tensor I bra, because remember in our in our tensor product rule, we say we have A tensor B multiply C tensor D equal to AC tensor BD. And the important thing here is those A, B, C, D can have quite arbitrary dimension. Only requirement is B multiply D should be defined and A multiply C should be defined. And so here we use the IK I bra is IK vector times this I bra vector by matrix multiplication rule. Okay, so this outer product can be viewed as just this column vector multiplying this row vector. Okay, and similarly we break this IK I bra into this IK times I bra. Okay, so we break up those two things, and then on the first register we just have identity equal to identity times identity, and identity equal to identity times identity. Okay, and then to make things a bit easier, let's define this matrix. Let's actually wrong name. Okay, so it's let's see, row AB. Yeah, I should not call it row A. So it should be called row AI, maybe row AI bar, because it's different from the row AI before. Okay, so here maybe row AI tilde. Okay, row AI tilde, row AI tilde, row AI tilde. This is row AI tilde is actually PI times row AI. Okay. And anyway, it's not too important here. For now, it's just a number. But so row AI is this row AI tilde is basically what we want, and it's already in middle. It is I tensor IK I tensor identity tensor I bra times row AB times identity tensor IK. And then this thing, as we know, it should be something only on system A, because the dimension on system B becomes just 1, because you have a row vector here and a column vector here, so the dimension on system B become 1 here. Okay, so you have this row. I guess technically you should not say system B anymore. It's like on the second step. On the second slot, it becomes dimension 1. Okay, so this thing only has a value on the register, on the first register. Okay, and yeah, as we said, this thing is this row AI and well, tensor 1. Yeah, row AI tensor 1. I guess here we kind of overuse the notation of whether you tensor 1 or not, but I guess it's okay. And anyway, in the middle part, it becomes row AI tilde. Yeah, in the middle part, it becomes row AI tilde. And then we still have these two vectors left behind. It has t tensor I and yeah, identity tensor ICAT and identity tensor IBRA. Okay. And now we see that those two things can commute because identity tensor, so because on the first register, those two things commute because identity commute with anything. And on second register, they also commute because here 1 is just a number. Number commute with anything. So 1 commute with this identity, with this ICAT. And so those two commute, and basically we got what we want. So we have now we have I tensor ICAT and I tensor IBRA here. And then those two things can multiply together. We have identity multiply identity equal identity. And we have K bra here, and so it becomes K bra here. And yeah, then finally we do our tensor multiplication rule once again. On the first register, we have row I tilde times identity become will still your row I tilde, which is this thing. And I guess here we rewrite our a bit of overuse our notation. So we say it's also this thing tensor identity. Okay, and yeah, so this become row I tilde. This row I tilde on the front and tensor this projector onto I on the second register. Okay, so this is how you do this carefully. Okay, and yeah, and that's almost finish all we want to talk about reduced density matrix. I guess reduced density matrix, it should really have these three properties. So if we have two-party system, two-party state row A, B, and then we think about it has some reduced density matrix row A, and so it should have these three properties. And I guess you didn't approve here, but we have kind of a proof here, and then hope for proof. I guess it's left out the exercise, and I think it's also in the book. Okay, although the book proof is a bit weird. Yeah, the book proof, I think it's quite complicated, but it should be correct. Okay, but anyway, it should have these three properties, and I just state them here without proof. First is that row A will describe all the measurement outcome that you can do on system A. And second is that we kind of assume it is true without proof, but you can also prove it rigorously. So those two proofs, I think you can do in homework if we find time to find a slot to put in prove homework. And the second property is that any operation on system A will, any operation you do on system B will not change this row A. Okay, and then third one is you can also track what you do on system A with this reduced density matrix row A. So if you do a unitary U on this system AB, then unitary U on system A on this state row AB, that it will evolve this reduced density matrix row A to this U row A U dagger. So this is so basically this thing is you do U tensor identity on row AB. Okay. And yeah, so those are the properties of reduced density matrix, and because of these three properties, we think a reduced density matrix row A describe all the quantum properties you have on this on system row A when you have this two-party state rho AB. Okay, and yeah, I guess a bit more thing here. I want to say about this notation. So a bit of notation is that for describing. So now we have a system with multiple parts, and so we will do this notation. That is, we will mark the mark the subsystem. So mark which subsystem your state is on with this superscript with your register. So if the state is on register AB, then we have this superscript AB, and you see we have this superscript A here. And so we say this here because this is sometimes people will do different things. Sometimes people will label their subsystem as a subscript also. But we'll try to be consistent throughout the course and have the subsystem as a superscript, but I will not be 100% sure. So sometimes the rho AB, you will see people like this, and it's fine. And you can see, you can see also this as some advantage of using this is because it doesn't look like exponential. Because you have a superscript, a lot of the time it's like rho to the AB power, but this is not rho to the AB power. This is a rho on AB system. Okay, but notation overloaded. Sometimes you have too much subscript, then we want the superscript, and sometimes you have some exponent on the top, then you want the subscript. So we try to be consistent here, but just know that when you read papers, sometimes people write register on down here also. Okay. Okay, then that's the end of this slide, and we can go to next topic about these density matrices, and that will be, let me try to save here, and that will be this idea about streaming decomposition and purification. Okay, let's do this. Okay. So small recap. We talk about density operator. Wait. Sorry, I think I opened the wrong slide. It should be this one. Okay, should be this one. Wait. Okay. So now it should be correct. Okay, and so we talk about density operator, and let's go to something slightly unrelated, slightly far away. That's this streaming decomposition. Okay. And but it's still talking about two-party system. So streaming decomposition is a very nice way to describe a two-party system. So now we back to a bit easier case. So we say we have a two-party system, so with system A and system B, and we assume they have a pure state. Okay, so we have a pure state between system A and system B, and it's a bipartite system, means that it has a two-part, part A, part B. And then there is a nice way to describe this any entangled state between system A and system B if there it is a pure state. Okay, and so this nice way is this. Okay? So the streaming decomposition is a bit of a theorem, says that any pure state between system A and system B can be written as a streaming decomposition. And it's just this summation I and some non-negative real number lambda I here, and some IA on system A tensor some IB on system B. And so here the important things here are, I guess I should mark the important part as red. Okay, important part is IA, the set of state IA is also normal basis, and the set of IB is also normal basis. Okay. And also something that's not very obvious here is that they share the center of I here. Okay, so this thing. Okay, so when we summation I, we are summing over same I on IA and IB means we have 0A, 0B, then we have 1A, 1B, then we have 2A, 2B, etc. Okay, so we are summing through the same, we're increasing the same indices here, so these are the same I here. Okay, so important here is same I, you have some lambda I for every I, and then IA and IB. Okay, and this is not just writing A in any computational basis and B in any computational basis, because if you do so, then say so if you do so, then you will have this is a different thing. If you have any computational basis on A and any computational basis on B, then you have some ij here and the lambda ij, some ia here and the jb here. Okay, so the special thing here is A and B are sharing the same I here. Okay, and then go back to a bit of a streaming decomposition. Here those lambda I are non-negative real number, and they satisfy summation I lambda I squared equal to 1, and they are called streaming coefficients. And so what's nice about this streaming decomposition is they will tell us a lot about how season A and season B are entangled with this pure state side here. Okay, as we'll see. Okay, and but before that, let's go back to density matrix a little bit. For now, this is only pure state. And let's quickly go to this reduced density matrix. So we see that from this streaming decomposition, we can calculate the reduced density matrix on season A and the season B very fast. Okay, say we want to calculate this reduced density matrix on season A. Then we do partial trace on this thing. Okay, and partial trace on this thing. So here, this is why we have this here. So first we need to write the density matrix on season A, B. So this is side, and we have some ij here, lambda I, lambda j, and IAIB and JJB. And then here we do partial trace. Then we need to use we can use the season B is also normal. So when we have IB inner product with JB, you have 1 only when I equal to J, because IB and JB are also normal. Okay? So this is an extension of the result that we said before. Okay, so when you do partial trace on the B part, you only pick out when I equal to J. Okay, so in the end, your summation only have some I. So some I lambda I square, and the B part gets traced out, you left with IA. Okay, so lambda square from this lambda I lambda J, because now I equal to J when sum over J. Okay, so this is the reduced density matrix on system A. The summation I lambda I square IA. You see that you can quickly see from your streaming decomposition to see what's your reduced density matrix. And not knowing that, you can also do a similar thing on row B, and you get similarly you have this lambda I, some I lambda I square, and IB. And then you see that those two things are very similar. Okay, so those are already eigen decomposition between row A and row B, and also you see they have the same set of eigenvalues. So the eigenvalues are just this set of this lambda I square and the set of this lambda I square here. Okay. And you see that the row A and the row B has the same set of eigenvalues. Okay. And this means that whenever you have a pure state on your row AB, okay, whenever you have a pure state on your row AB, then a lot of property on row A and row B will be the same, because they will have the same set of eigenvalues. Okay. Okay. And so that's the first thing we know from streaming decomposition. Any question? If not, we have 10 minutes. I guess we can run over the proof very quickly. So let's first prove that everything has a streaming decomposition. As we said, this is not true. Not true if we just write down as a arbitrary arbitrary orthonormal basis on C7 A and B. And yeah, so with our proof, the proof has two direction. Yeah, so yeah. Sorry, proof only has one direction. Sorry. Yeah, proof. So to do a proof, let's do this arbitrary decomposition of C7 and C7 B. So we can try to find whatever orthonormal basis on C7 A and whatever orthonormal basis on C7 B. With we call it J and K. It's a bit of sloppy notation, but it's okay. So yeah, so we can write any state into this orthonormal basis that's J tensor K and with some coefficient AI AJK. Yeah. And then we try to eliminate the sum JK into just one summation. Yeah. And here we need to use linear algebra thing that we didn't really review in the beginning of our slides, but well, it's nice to know, but we will not use it too much. I think it's probably the only time we use in the course here. And anyway, this is a linear algebra thing, says that for any matrix, you can write it in this singular value decomposition. And what we are writing on is this matrix A. And so what's a singular value decomposition is that, so you have whatever matrix A, you can write it as a product of UDV. It's a bit like eigenvalue decomposition, but it's stronger because you can use this on any matrix. Any matrix A of dimension whatever m times n, and it don't need to be normal or anything. So any matrix A can be written as singular value decomposition, where this U is n by m unitary matrix, and V is n by n unitary matrix, and then you have this weird D matrix, which is so-called diagonal matrix, but it's not fully diagonal. Diagonal means that, so because it's dimension m and n here is another same. Okay, so D also dimension m times n, and its diagonal means that it's diagonal until the diagonal hit the boundary. Okay, so you have the diagonals that are non-negative elements. Those are called singular values. Okay, I guess I should say those are singular values. Yeah. So those diagonals are singular values. Okay. So you have those singular value matrix that multiply a unitary and another unitary. Okay. And anyway, that's what we want to do on this matrix correspond to coefficients AJK, and they become UDV, and AJK will be UJI and DII and VIK. And here, for now, we are not doing very well. We have even more indices here. We want to reduce indices, but this will pay out later. And anyway, but now we have something nice here. So we use that D is diagonal here. So we only introduce one HR index instead of two, because usually whenever you have a matrix multiplication in between, you need to introduce the HR dummy variable. So here and here, but because D is diagonal, you only have I HR indices here. Okay, and anyway, now we have three indices. And as we always like to do, now we want to change the order of summation. I guess here we already changed, so we have a summing over I on the alt. And now we want to sum JK to get rid of those indices. And so we want to sum JK, and what's nice is, well, J only depends, so only this part depends on J and only this part depends on K. Okay? And so you can just define sum J Ujij as a vector, and you can define this also sum K Vikk as a vector IB. Okay, so this thing depends on I, and so this thing depends on I. This thing depends on I. This thing depends on I. Okay, and yeah, and you define lambda I just as this dii, and so you kind of just synthetically eliminate these JK indices, and you become your state become the sum I lambda I and IAIB. But we also need to check a bit more. We say that the IA and the IB need to be orthonormal to be orthonormal bases. Okay? So IA need to be orthonormal to each other, and IB need to be orthonormal to each other. And so we use another property of singular value decomposition. We use that U and V are unitary. So because U and V are unitary, so this IA equal to sum J, Uj, Ij. This thing is a unitary transformation from this basis J to this basis IA. And J is also normal, so IA is also normal. Okay. So because U is unitary, and IA are also normal. And similarly, because V is unitary, IB are also normal. Okay. So this complete our proof of yeah. So here basically we already complete the proof of our streaming decomposition. We see that any state, you can write this in this arbitrary orthonormal basis. Then you can do singular value decomposition on your coefficient matrix and change it into this streaming decomposition basis. And where you are summing over only one indices, but the state on A and the state on B are still also are both orthonormal bases. And here is a bit side note on streaming decomposition that we don't quite prove. And yeah, so this is decomposition because singular value decomposition, basically you see it come from singular value decomposition. And most of the time, singular value decomposition is unique, and the mainstream decomposition is also unique. And in particular, we have a bit of statement here. So we say if those lambda I are not degenerate, so if they are all different, then streaming decomposition will be unique. And also the set of lambda I will always be unique. That's just from singular value decomposition. The singular values are always unique. Okay? And singular values are always unique. And yeah, as we said, if they are not degenerate, then also the direction of the your singular value decomposition will also be unique. Yeah, so that's a nice property to know about streaming decomposition. Yeah. And here we have a bit of terminology associated with streaming decomposition. So this spatial basis is usually unique basis IA and IB are called streaming basis. Okay. And those lambda i's are called streaming coefficient. Okay. And then we have a number. Okay, and we have this a bit weird definition. We have also the streaming number, which is a number of non-zero lambda I. Okay, it's yeah, this part is a bit tricky whether you want to include lambda I equal to 0 in your definition. As in this notation, it's not very clear whether you include lambda I equal to 0 or not. Okay, and yeah, but yeah, I guess here, yeah, here we usually include, but include in our course. I guess this depends on context, but. So we usually include lambda I equals 0 as lambda I in lambda I in this course, but this is a bit of ambiguous. Okay. But anyway, so back to the streaming number. So the number of non-zero lambda I. Okay, and so this thing. And is called a streaming number. Okay. And yeah, but some people sometimes I think also in the textbook is not very clear on this part. I think the textbook only include the streaming coefficient as the non-zero lambda I. Okay. Then the streaming number is just the number of lambda I here. Okay. So it's a bit confusing, a bit ambiguous here. Okay. And yeah, that's 2 minutes. So a good thing about I guess a good motivation for streaming decomposition is that once you write down streaming decomposition, you can check whether a state is entangled. And we have a really short time here, so we just state the result. So if the streaming coefficients, if the stream number is just 1, then your state is not entangled. And the stream number is greater than 1, then your state is entangled. Okay. And yeah. Yeah. So if your stream coefficients are those 1, 0, 0, 0, and with streaming number 1, then your state will be a product state. Okay. This is if only if. So this is the thing that people use most. So I guess I should circle this here. Okay. So this example is why people want to count streaming number, because if your streaming number is 1, then your state is a product state. And if your streaming number is not 1, then your state is not a product state. I guess if direction is a bit easier, so if your streaming number is 1, you can see that you only have a non-zero lambda I here, and in fact it will be 1, so your state is just IA tensor IB, and it's a product state. And the other way around, you need to work a bit harder to prove it. Okay. And yeah, so that's why we like streaming decomposition. It tells us how entangled your pure state is. And then we have a bit of example that you can try out for you with your streaming decomposition, and we'll walk them through next time. Okay. So any question? Otherwise, we can stop here for now. Okay, let's stop.等一下，我先关掉录影以后。奇怪的原因是，好，现在这应该就先把应该没错，可以。